Next, we're going to take a look at a weak acid, strong base titration. So in this one, we have 30 milliliters of 0.5 molar acetic acid, and it's titrated with 0.5 molar sodium hydroxide. The Ka, which is going to be significant now that we've got a weak acid, is 1.8 times 10 to the negative fifth. So same general process as the last example that we did, except in this case we've got a weak acid, strong base. And there's going to be some different equations going on during this one. So the titration equation, what's happening during the titration is we have acetic acid, which is H, C2, H3, O2, and that's going to be reacting with hydroxide. You guys should be familiar enough with strong acid, or strong base, weak acid reactions to know that that's going to produce acetate, H3, O2 minus, plus H2O. And also, and this reaction, notice it is going all the way to completion. Okay, so we're considering this as a strong base, and so it can get those H pluses donated to it to generate water and this acetate. However, also going on at the same time, the acetic acid that's in there, HC2, H3, O2, is at equilibrium with C2, H3, O2 minus, plus H plus. So this being a weak acid, it is at equilibrium with itself, with its ion, and H plus. So both of these are going to be happening simultaneously, and that's what makes this reaction a little bit trickier, because we have a lot more things going on, rather than just H plus and OH minus making water. So our first thing we're going to want to do is find the initial pH at 0.5 molar acetic acid. At this point, you guys should know how to find the pH of a weak acid fairly quickly using a couple different shortcuts. You should recognize the equation. I'm going to go through and solve this just like we did back at the beginning, step by step. So hopefully you know how to do it, but if you need a little extra reminder, this is how you would solve for it. So we're going to use the pH of a weak acid solution, so the ice table. So we're starting with our acetic acid, and we need to figure out at equilibrium how much H plus and how much acetate there is, and we'll use this H plus to calculate what the pH is. So initially we had 0.50 molar acetic acid, and 0 of this and 0 of that. This guy is going to have to decrease by x so that these two can increase by x, which means at equilibrium, this is going to be 0.50 minus x, and both of these will be plus x. So if the Ka is 1.8 times 10 to the negative fifth, we can think, alright, so if we have 0.50 minus 1.8 times 10 to the negative fifth, what's the value going to be down here? It's still going to be 0.50. So that minus x we can get rid of. And a chemically savvy student knows already that you can get rid of that, recognizes that in weak acid calculations the minus x is almost never significant. Okay, so with those values we can find the H plus concentration. So Ka is equal to the concentration of H plus times the concentration of the acetate, and we're going to divide that by the HCH3COO concentration. Sorry that I write my acetates and my acetic acids different every time. I don't know why I do that. So if we solve with the values we have, we know that it would be x times x, or x squared, divided by 0.50, and we got rid of that minus x, don't need to put it in there. And we can solve then for H plus. Let me clear some room. So then the concentration of H plus is going to be equal to the square root of 0.50 times the Ka, which is 1.8 times 10 to the negative fifth. So our concentration of H plus is 0.0030 molar, so very low concentration of H plus. So if we do the negative log, of the concentration of H+. That's going to give us the pH. So we're just going to take this value and plug it in down there. And our pH is going to equal 2.52. So that would be our initial pH of this solution of acid. So now let's see what the pH will be after we add 15 milliliters of our strong base, the sodium hydroxide. So same initial step as a strong acid, strong base. We're going to find the number of moles of acetic acid and the moles of sodium hydroxide that are in the solution at this point. So the moles of acetic acid, we had 0.030 liters of acetic acid in the solution, or we had that many liters of the solution, and there's 0.5 moles for every 1 liter. So that means we're going to have 0.015 moles of HCH3O2. And for sodium hydroxide, we've added 0.015 liters of the solution, and it's 0.50 moles for every 1 liter, which means we have 0.0075 moles of sodium hydroxide. Okay, so this is a strong base, so really it's just the hydroxide that we're concerned with. This is a weak acid, though, so it's not just going to be the H+. This entire thing is together. We're going to consider that the hydroxide, the OH-, is going to be ripping the protons away from the undissociated acetic acid because there's such a small number of already ionized H+. So to figure out what the new pH is going to be, what the concentration is going to be, we're going to have to first figure out the equilibrium concentrations of acetate and acetic acid. So initially, we are starting with 0.015 moles of the acetic acid and 0.0075 moles of the hydroxide. So our limiting reagent is going to be the hydroxide. This is the smaller one. Both of these are starting at 0. Water we're not really concerned with because it's a liquid. This one will decrease by 0.0075. This one will decrease by 0.0075. And this is going to increase by 0.0075. So now we have at equilibrium 0.0075 moles of acetic acid. We'll have 0 hydroxides left, and we have 0.0075. Okay, so that's how many moles we have, but moles don't really help us much for further calculations. We need to get that into molarity. So our new volume is going to be the 15 milliliters that we just added, plus the 30 milliliters we started with. So that's 45 milliliters total, which is 0.045. And so if we find our concentration of HC2H3O2, it would just be the 0.75 divided by the 0.045, or the 0.0075 divided by the 0.045. And that means we have 0.17 molar of the C2H3O2. And the concentration of our acetate is C2H3O2 minus. That'd be the same thing. It would be the 0.0075 divided by the 0.045 liters. This would actually be the same concentration now. And this one up here should be an H right there, sorry. Alright, so what we have here is we have acetic acid and its conjugate base. Wait a minute. We have a weak acid and its conjugate base. Hold the phone here. Weak acid, conjugate base. That makes a buffer. We have a buffer at this point. That means to find the pH, we can't just do the old negative log calculation. We have a buffer on our hands. And how do we find the pH of a buffer? That's right, Henderson-Hasselbalch. So the Henderson-Hasselbalch equation tells us that the pH of a buffering system is going to equal the pKa plus the log of the concentration of the acetate divided by the concentration of the acetic acid. So we just found both of those in our ICE table. They were 0.17 and 0.17. The Ka is 1.8 times 10 to the negative fifth, so we can find our pH pretty simply now. So pH would be the negative log of 1.8 times 10 to the negative fifth plus the log of our concentrations, which was 0.17 molar, divided by 0.17 molar. And so it would just be plus the log of 1, which would be 0. And so the pH is going to equal the pKa in this case. And that means the pH is equal to 4.74. That was fun. That was a lot of fun. So you see how buffers can be formed accidentally just by doing a strong acid, strong base, weak acid titration. And that will affect our calculations, and you need to be able to recognize when that buffer is formed. Alright, let's take a look at the next step in line. So this next part, we're going to find the pH at the equivalence point. So the equivalence point for a weak acid, strong base, would be the point when you have equal numbers of moles of sodium hydroxide and the acetic acid have reacted. So when the concentration of this equals the concentration of that guy, the number of moles of this guy equals the number of moles of that guy. This would occur when we add 30 milliliters of the sodium hydroxide and, 30 milliliters of the sodium hydroxide and 30 milliliters of the acetic acid. At this point, you would have equal molar additions. However, even though the hydroxides have ripped the H plus ions off the acetic acid, this does not mean that we are neutral. In fact, we will not be neutral, so pH will not equal 7 for this particular titration. So what's going to remain in the solution at equivalence point is going to be the Na pluses, the sodium ions, and the acetate ions. So the issue is, if we go back and look at the effects of the the effects of the pH of salts, if we have the conjugate base of a weak acid, a conjugate base will accept protons from water. So a conjugate base of a weak acid is a slightly stronger base than its parent acid. So that means it can ionize water, and what it's going to do is it's going to ionize water to create those hydroxides. So we talked about this back when we talked about the pH of salts. This is where that comes into play. So all that's left in solution, Na+, and then this acetate, and that acetate will hydrolyze the water to create more acetic acid and the hydroxides. And it's these hydroxides that are going to affect the pH. Okay. Even though this right here is acetic acid, it's unionized acetic acid, so it's not increasing the H plus concentration. The only thing we're doing right now is increasing the OH minus concentration. Alright, so we need to find the pH then for this particular equivalence point, with this reaction going on. So we have the conjugate base of acetic acid reacting with water to produce these two guys right here. So the first thing we're going to need to do is find the Kb. Since this is now a basic reaction, we're not going to be using the Ka anymore because we're not dealing with acetic acid, we're dealing with its conjugate base. So this is where we have to go back and remember a couple things. And the thing that we're going to remember is that the Ka times the Kb equals the Kw. So this would be the Ka of the weak acid. This would be the Kb of its conjugate base. So acetic acid's Ka, we said, was 1.8 times 10 to the negative fifth. Here's its conjugate base, and that's what we're trying to find the equilibrium constant for this particular reaction. And Kw 1.0 times 10 to the negative 14th. So we can rearrange this equation and say that Kb is going to equal the Kw divided by the Ka. Isn't it fun how all those pieces of information that we learned earlier in this unit are starting to come together into one mega equation? This is a blast. And so Kw 1.0 times 10 to the negative 14th, we can go ahead and assume it's at 25 degrees Celsius. As long as we use the proper numbers the whole time, 1.8 times 10 to the negative fifth. And so that means our Kb, our equilibrium constant for this particular reaction up here, the now basic form of the conjugate, would be 5.6 times 10 to the negative 10th. But in order to be able to do anything with this number right here with our equilibrium constant, we're going to have to use it up here in this equation. Use Kb to calculate what the new concentration of OH minus is. In order to do that, we need to know how many moles of acetate we have in the solution at this point. So we're at the equivalence point, which means we have taken our initial 0.015 moles of acetic acid, C2H3O2, and we have reacted all of it, which means the sodium hydroxide ripped all of these H pluses off and left us with the acetates. And since we've reacted all of this, it's a 1-to-1 ratio. That means at the equivalence point, we would have 0.015 moles of the C2H3O2 minus. So there's not going to be any of this vinegar or acetic acid left quite yet. All of it's going to have reacted to form this acetate. So at this point right now, we have this many moles of the acetate. Okay. So now let's find the pH at the equivalence point. So in order to find the pH, we're going to have to find the concentration of the C2H3O2 that we can use in the Ka equation. So at the equivalence point, we have added 30 milliliters of sodium hydroxide and 30 milliliters of acetic acid. So that means our volume is going to be 60 milliliters. So if we have 0.015 moles of acetate, and we have 0.060 liters of solution, that means our concentration is going to be 0.25 molar. And that would be our concentration of acetate. Let's throw down a nice table here with our Kb equation. So we're going to be dealing with this acetate. It's going to hydrolyze the water to produce these hydroxides and the acetic acids. So we have 0.25 molar acetate. We're not concerned with water at all. We're going to start with 0 of this and 0 of that. So before it's hydrolyzed any of the waters, it's going to have to decrease by x, and both of these will increase by x. So that means at equilibrium, this is going to be 0.25 minus x, this will be x, and this will be x. So Kb that we found earlier was 5.6 times 10 to the negative 10th. And if we real quick just think about this, subtract 0.25, subtract 5.6 times 10 to the negative 10th from that, you're still going to wind up with 0.25, and so that minus x is irrelevant. So now we can go ahead and find out what the concentration of hydroxide is going to be by plugging it all into the Kb equation. So Kb is going to be the concentration of HC2H3O2 times the concentration of hydroxides divided by the concentration of C2H3O2, the acetate ion. Okay, and if we solve for the hydroxide concentration, OH minus, it's going to equal the square root of 0.25 times that Kb value we got, so 5.6 times 10 to the negative 10th. So that means the hydroxide concentration is 1.2 times 10 to the negative 5th molar. So now that we have that value, we can use that to calculate the pH for the solution at this point. And so to find the pH, we're going to need to find the pOH first. So let's take the negative log of that OH concentration, which would have been 1.2 times 10 to the negative 5th. So that's going to give us the pOH, which will be 4.92. Then, of course, to get the pH, it would be 14 minus 4.92. And so the pH of the solution at the equivalence point is going to be 9.08. So as you can see, when we're titrating a weak acid with a strong base, at the equivalence point, so at the point where the original acid equals the concentration of the OH that you have added, the pH is above 7, so it ends up being slightly basic. And this is common with all weak acid strong base titration. So if you're asked, hey, you're doing a weak acid strong base titration, what will the equivalence point pH be? You can predict that it will be above 7 because of the production of that salt that's going to hydrolyze the water. And now that we're past the equivalence point, let's go one more step and find the pH after 40 milliliters of sodium hydroxide were added. The same business as usual. We're going to start out by finding the moles of the acetic acid and moles of the sodium hydroxide, and then from there go on to find our pH. And the moles of acetic acid is still the same. We already did that calculation. No need to do it again. 0.015 moles of acetic acid. And then the sodium hydroxide, we had 40 milliliters of that at this point, so 40 milliliters, and it is 0.5 molar, which means we have 0.020 moles of sodium hydroxide. Not going to do the calculations. I'm assuming that you guys know how to do those by now. So let's take those numbers then and look at what happens. So let's find the pH after this occurs. Got to do the ice table, so come on, use the pen, Jones. 0.015 moles of acetic acid and 0.020 moles of hydroxide. We're starting with 0 of the acetate ion, not concerned with water. So now if we take a look at these two numbers, our limiting reagent now is going to be the acetic acid, because we've passed the equivalence point, so we're going to have an excess the hydroxides. So it'll decrease by 0.015, decrease by 0.015, and increase by 0.015. So then at equilibrium, this will be 0. We'll still have 0.005 moles of hydroxides left, and this will be at 0.015 moles. Alright, and so our new volume is going to be 70 milliliters because we added 40 to 30. And so if we have 0.005 moles of hydroxide in 0.070 liters of solution, that means we have 0.07 molar hydroxides. So then on to the pH. First we've got to find the pOH. So pOH is going to be the negative log of our OH minus concentration, which was 0.07 molar. And so our pOH is going to be 1.2. But we want the pH, so 14 minus 1.2 is going to give us our pH, and it turns out to be 12.8. So we are now in a basic solution past the equivalence point because we beat it all out and moved up with the higher hydroxide concentration. Alright, here is the titration curve for a weak acid strong base titration. So once again, you should be able to recognize these titration curves based upon how they appear, where things lay out. So notice with this titration curve in the acid range, so down here, this is where you were forming that buffer. And so we had a very slow increase in the pH. And then this little range right here where it shoots straight up, notice how it isn't near as tall as it was for a strong acid, strong base, and that's because of this buffering zone. So because we formed a buffer down here in the acid range, so pH buffer below 7, we had that kind of steady increase right there. We had the sharp increase that marks where the equivalence happens, and so the center in the middle of that upshoot would be right there, and so that's our equivalence point, and notice how the equivalence point is above 7. So it's a basic equivalent point in the basic range, and that is because it was a weak acid with a strong base. And then up here, it goes back to that kind of almost flat line, just like in the strong acid, strong base, because there's no longer that buffer system being created, and so it just gradually increases. So with a weak acid, strong base, we have a buffer down here, and then a normal line up there. Our pH at the equivalence point is above 7. Alright, so that was a weak acid, strong base titration. The same general principle if we were to use a weak base and a strong acid. Okay, we're going to create that buffer, we're going to have a salt that's going to hydrolyze. The only difference is really where the buffer's created, and then the pH of the salt that's created as well. So if we were to do, when we did a strong acid, weak base, we created a buffer in the acid range. Okay, so we created that buffer down there. And then our pH, the equivalence point, was above 7 because of that acetate, CH3COO minus, that hydrolyzed water to produce those hydroxides. So if we were to do this with a weak base instead, so a weak base would create a conjugate acid, so let's say we used ammonia. Ammonia is going to create a conjugate acid, like NH4, and that would be a stronger conjugate acid. So here would be the salt that it would create at the equivalence point, and so that would create a pH that is below 7 instead. Okay, so it's going to generate those H pluses. So let's take a look at what that titration curve would look like. I don't have a picture of it, we can draw one in pretty easily. So if we're starting with let's just call this a weak base, and a strong acid titration. So if we're starting with a weak base, that means our pH would start up here, okay, in the basic range, and we would be creating that to buffer once again. So just like we had that buffer right there with the weak acid, strong base system, we're going to create a buffer up here with our base as well. And so it's going to buffer, but it's going to buffer in the basic range. And so we'd get kind of that steady decline, and then our equivalence point would happen right there, and then it would almost flatline with just that steady decrease right there. So the difference is our buffer zone would be up here in the basic range. Our equivalence point would happen down here. Oops. In the acid range. And so it's just kind of flipped right there, but same general buffer zone. We get that salt that hydrolyzes right there and creates the slightly acidic equivalence point, and then just that general decrease right there. So you should be able to recognize now a weak acid, strong base titration, a weak base, a strong acid titration, and a strong acid, strong base titration.